So remember from last time that we took a lot of time in creating these queues. It's data structure that allows you to have a set of elements. And what is important is the person who is at the front of the queue, who gets treated first as he's queuing or she's queuing, and the person who is at the end of the queue, who has to wait quite a long time perhaps, but was the last one to arrive at the queue, right? So it's a FIFO buffer basically that we introduced, and we introduced two of them. To remind you again, the first one was implemented by just using a dynamic array. We created an array of a certain maximum size, and in this array we implemented this FIFO buffer, or this queue. Now the problem there is that we sometimes waste memory because we reserve quite a lot of memory and probably don't need it all. Or sometimes you bump into the problem that you have actually an array that is only that large, and if only it would be a couple of bytes larger, it would have fitted, but no, you had this maximum. So therefore we introduced also this linked list implementation, which we called unlimited queue. And this queue is basically a linked list of class objects that also have a pointer to the next object. And with two pointers, one pointing to the head, one pointing to the tail, we created then another implementation of a queue. Both of them have their own purposes. You know, by knowing how they're constructed, you can see in which cases one would be better than the other, for instance. But this is typically what happens all the time when you're programming. The limitation, however, of these two queues, and that's what I wanted to show on this slide, is that if this is something that we did with integers, like a basic type, typically you would of course do this with objects of your own class. You want to group data together, and that would perhaps be necessary to put into a container in a particular way or form. So the way we want to do this here is in a more delinked fashion, so that the container, the things that we already done in Q and UQ, the implementation of the container is one thing, but the data type is another thing. So if only we could disconnect those two. But up until now, we did not know how to do that, because if we had now, instead of an integer class of our own choosing, we would have to redo all that work again for these two container classes. And that is a lot of work. It is duplication of code, which is also not very nice. And at the same time, it's kind of goes against loads of paradigms in programming. We rely a lot on classes that others have made, where others have made sure that these classes are very efficient, well done, obtained, maintained, and ready to use. But if you would redo all of that work or copy all of that work and insert your own data types, that would be a lot of work and a lot of copying with lots of room for error, and that would not be good. So therefore, in the early days of C++, already people started thinking about templates. Templates allow to do this. So you first think about how you are creating a container of a particular class without specifying what class this is. And then only later you fill in what type of class you really were talking about. And this is what a container is. And the container is something that happens while the compiler is looking at your codes, and it's basically implementing your or re-implementing your code for you. So here's a very simple example of how this happens. So this is the original code. And by the keyword template, you tell C++ that from now on, what follows after that is a template definition. And you can use this for either a function or a class. That means the next function that follows or the next class that follows is going to use templates. And a template is kind of like a placeholder in which any type of including also a class or basic types of variables, can be mentioned. Typically, this is done with class. In a second, we'll see also there's another option between these bigger than, smaller than braces, and then a name that you can give yourself. So this T is a name for the parameter of the templates. This is denoting that you're going to use a class that is only defined later, but that for now will be called T for templates. And then for this function, we're going to use this T as if it was a type. like int or car, or a particular class that we have written, or that somebody else has written, like std string, for instance. So our function is called maxof, that's our name. It returns something of a particular type that we'll later define, and it will take two parameters, x and y are their names, but their types is also something that we will later define. Right? So the yellow, as usual, is what is new, but the t is basically a parameter of a template, which we know, or which C++ knows, is a template because of this definition right here. The rest is as we've had before. We can, of course, in the body of this function, create also this type. We can do ti, for instance, and then we have created a variable I of type t. And again, this t will then be later on filled in by the compiler. So in our main function here in this example, we use this maxof function, and that is the second part of what is new here. After the name of this function, we have to declare, and when this is a class, after the name of the class that we then define, we have to then say which template we're going to fill in. This can be an integer, this can be a character, it could also be our own class type. So in this case, we want to create a function maxof that uses integers, and therefore we give it integers, 12 and 24. Now, when this is met by the C++ compiler as it is parsing our codes, then it will replace this using this information with this over here. So it is almost as if there is one function called maxof that is using integers, and then later when it meets this one, there is yet another function called maxof as well, which is using characters. And this is something that we could have done as well, right? We can overload functions, but in this case, we're doing this through templates. That is the quite important part. And it is done at compile time. That means as the compiler is going through your text file and creating the machine code for the executable, it basically creates out of this, these two things and plugs them in your code. Right? Yes?
Would that work like with the classes? Because where in the class you should implement the conversion operator.
With the class... Oh, right, with the bigger than and smaller than, yes, you're absolutely right. Then we would need to have this operator defined for those classes. Yeah, otherwise, of course, the compiler, so if we would have our own class, say class A, and we define this as a class, so later you would want to create an object small a of class A, for instance, and you would then fill those in here, then you would get definitely a problem because this particular function uses an operator that is not defined for these classes, objects of these classes. Yeah. And you would need to do this yourself. And how to do this is coming in a couple of slides. So thank you for that question. Yeah. Okay, so this is the revisit of our queue example. So in this case, we kind of make sure that our queue example, it's still a dynamic array, the way we implement it, because for some reasons, or for some applications, this is well motivated. If you know that your queue will never be bigger than 100, for instance, why would you create a linked list that has some overhead that you definitely don't want? In this case, you could just create, for such a small array, definitely a dynamic array. And that's what the rest of the code is looking very, very similar, probably to what you've seen already, but we're going to plug this as a queue of any data type. And just like we did this in the previous slide, we can then, before our class definition, so this is a class that is using templates, not a function using templates as the previous slides, we announce that we're using template here, namely the one that we call data, not t in this case, but data. And that means that in the rest that follows for this class, everywhere we have data with a capital D, we're going to then replace this with a type later on, or the compiler will do that for us. That means if we're going to use this queue, we'll have to use this is smaller than is bigger than braces, and then in between those, put in our own type, like an integer, or a character, or a double, or a class of our own type, if we then don't infringe operators over here that are necessary. Which in this case I think is not a problem at all for most classes. So we'll have exactly what we had before, but instead of our integer like we had before, we have data everywhere. And if we want to have a queue of characters or a queue of doubles or a queue of any type of other class, this would still work. Okay, so this is the template class that we then created. And there's almost no difference with our normal queue, except that here integer was replaced with data, and at the beginning we said we're using data as a parameter for our template class. And that is now a template class. And when we implement the methods that belong to our class, or the method functions, the member functions, I mean, then we have to do this in the CPP file typically as well. So also there, we have to then say, oh no, not in the CPP file, that comes later. So basically, we will have to say in front of each implementation of those functions that we are also there using the templates, using exactly the same template parameter, so that we know that data is being used. But also that is just the only thing that is different. There's not much else that is different from here. And then once we then use our queue, we can use it in multiple fashions for any type that we would like. So in this case, I create one queue, which is a queue of integers, and one queue, which is a queue of characters. And if our application says, you know, there is definitely one maximum queue that never will be overrun, then basically we can just say that. We can just give them a maximum. And then for our integers or our characters, we can just add new things to our queue. That is what we know we can do with the method put. And both queues are then being filled with 9 values. And then we can read those 9 values again for both of our queues, and you can see then how those would be different, right? So again, we use here an iterator that gets then again and again and again 9 times the head of our queue and removes it. Okay, that I think is fairly simple. We can kind of look at that in how I implemented it in the GitHub repository. Now all of this is in one file, and that I'm coming to in a second as well, but this is exactly what we had in the slides just now. So also here we basically have exactly the same. So if we have that and we compile this with, I'm not entirely sure, I think I used auto, so I would need 11. Yeah. And we run this, then we'd see that we get the same output, but on the left column is basically integers, and the right column are characters that are all transformed into characters into our console, of course. But it works, right? So this allows a queue to be used for any type of data. As long as this data is not, trying to get to a word here, but as long as this data is, like if you use a class, if there are operators being used on the elements of this class, of the objects of this class, that they need to be defined, as earlier already mentioned. Okay? So that is for our normal queue. The same goes for our unlimited queue. Oh, sorry, there's a question.
Looking at the max example that you showed the template, using templates for just method overloading.
Sorry, say it again. The max?
We kind of like use templates in order to prevent the writing of codes around and like using like method overloading.
Mm-hmm.
There was a time that you kind of like told us that you want to prevent implicit casting, such that we have integer, but we want to specifically use that integer and prevent users from applying floats. We kind of like create another also. So how can we implement that in that scenario?
So what I extracted from that is what is the difference to method overloading, perhaps even. Or overloading in general, because there are, I mean, especially if you look at the function, template functions, you might want to ask what is the difference between overloaded functions and template functions. But there is a big difference, because by template functions, you have the exact same functionality for different data types, whereas for overloaded functions, you can also use completely different functionalities, typically. And those are done at runtime, whereas templates are done at compile time. So they're not slightly different, they're very different. But that would be a very good question indeed. I think that is almost a philosophical question. When one would be better than the other, because there's definitely a common ground there. Sometimes you can implement things as templates as well as overloaded methods. That is true. But typically the two diverge and are very different. One is controlled by the compiler completely, one is done at runtime, and for overloading of methods or overloading of member functions or functions in general, you can choose to completely write something different in those functions. And that is not the case for templates. So templates are a little bit more restrictive there. Right? So think of templates a little bit like macros, like pre-existing things that you can plug into the compiler to help the compiler a bit. Okay. Any other questions up until now? Everything clear? Okay. So for the unlimited queue, there's the other thing here, because we used for unlimited queue another class. Right? So in there we used integers for both types. So we had a class where one attribute would be the integer that we would want to store, and the other one would be a pointer to the next object of our container, if you remember. So in this case, what do we do there, you might ask? And if you haven't asked that yet, you will at the moment, because there need to be two templates, basically. So, or two templates classes. One is the element, which, as I explained last time, we want to kind of keep hidden. You know, it doesn't matter that this class over here is visible or not. What users want to see is this uqueue, not this queue element. This is something that is kind of a helper class for our unlimited queue. However, in this case, and as in the previous one, we just have to declare it first that we're using it, but later we're going to do that somewhere where it's tucked away, where the user doesn't see this at first sight. And then our unlimited queue uses exactly the same notation as we had before. So we use a class, data as a parameter for our templates, and instead of integers everywhere, we have now data. The interesting thing is that we pass this data over here to our queue element. And this queue element is again using exactly the same template. So this is possible. So you can actually have multiple classes that use the same templates. And in this case, this template is also passed. It's using the same name for both classes. This doesn't mean anything, but the linkage actually happens here. The fact that we have a head and a tail pointer to queue elements that are made concrete right here. And this is not as obvious as you would think it is, because basically our compiler has to go through this definition over here. And if later we choose to have a queue of integers, then data will be replaced with integers. But it also means that here we will have a queue element that is then also concretized or specialized, they call this, as an integer class. And this is what is then visible on the next slide. So on the next slide for queue elements, also here we use exactly the same template definition, but this is often sometimes completely different. We could have called this T as well, like for our templates. But since in our uqueue we use data, we created head and tail as these very specific queue elements of a particular type, they will also be specified here. That means with templates, you can jump from one class to another, and the uqueue kind of immediately then defines the type that will be used for queue element right here. And that is a special thing for uqueue, and that's also the reason why I use this example, unlimited queue, not just because a linked list is rather neat, but it's also because we're using here a template class that is using another template class. And by using this one template class, you immediately define the type that is used for the other template class, or the class of the other template class, if you use classes in this case. So that is the special thing. The rest is kind of the same. So for all the methods, we use data again. Also here, it's specialized which queue elements we have. But that is more or less the same. You know, if you remember from last time what happens, none of that has changed really. But then if we use our unlimited queues, oops, I had a problem here. I should have UQ right here, not Q. But it would work exactly like it is. I can actually probably look at example 1 here. Right, so here we do have UQ. So it's exactly the same as we had for Q. We create an unlimited queue and then say we want this template to be filled in by an integer. And we specialize it towards an integer. Or here we specialize it towards a character. So that means int q and char q are completely different classes then. One is using an integer, one is using a char. That means over here when we use an integer, data is replaced by integer, and q element over here, as well as the q elements that we are using in the functions of this class, are all being replaced by an integer. And it means our q element in the second pass is then also being specialized as an integer automatically, so without us having to do anything. And that is this extra jump that I talked about. And the same will be then the case for our unlimited queue for characters. So since we define here that it's a character, over there where the class is defined, data will be replaced with character. This also goes for the elements. And the elements will therefore also be specialized towards a character. Meaning if we count integers from 1 to 9 and add those to our integer queue, or we count characters from 1 to 9 and put them into our character queue, that both will work because of those types. And again, just to hammer on the fact, we only implemented the code for our container once, right? That is the nice thing. We didn't create two classes. The compiler did this for us through the templates. Okay, so again, if we compile this, it should work. No, it doesn't. What did I do here? No matching constructor for initialization of, oops. Let's see if I can quickly fix this. I do have a UQ, so what is the problem? Maybe I made a mistake in the constructor up there as well. Yes.
You need to remove the numbers where you initialize both queues because we didn't specify the UQ with an integer in the constructor.
Oh, actually, right. Exactly. That's the point. So basically, I copy-pasted too much here. So there's no constructor with an integer over here. So that is the reason why we got those mistakes. Thank you very much. Or there's still something. Empty parentheses that we don't need. But that should not be the problem. Or was that it? Oh, it was it. Okay. Yeah, okay. It's interpreted as a function declaration. This is actually another thing that I wanted to address, but we'll do that later on. So this works. Let's try it out. Yeah, and we have exactly the same outcome for our unlimited queue. All right. Good. So that's our two queues being revisited. Let's move on to what can be done with templates, because that is not the end of it. Up until now, we've seen only one parameter for a template, and we used always class for that. This is almost, and that's why I put this link over here, there are some very fringe cases where this is not exactly the same, but it's almost the same as type name over here. Especially in the later versions, I think there's less and less difference between the two. That means typically I use class because that is the more common case. In the end, typically when you're programming in C++, you do create classes, and only after those classes you want to create containers that these classes fit in, or containers of where these classes fit in. So that is typically why I tend to take class here. But you might see also type name elsewhere on the web. And if you instantiate an object of a template class, then we call this sometimes also specialization. I think I just did already several times. That means as soon as you concretely say, I want Q, that is an unlimited Q, and I use the type double now, then we specialize this to the type double. And we know that in the background, our compiler then replaces this data with double, and we have now our class specialized and ready to go to be compiled into machine codes. And that is the use. Both as an object in our main function, as well as objects or other instantiations that happen in functions or methods that belong to classes, as we've had for our unlimited queue as well, for instance. Okay. Now, since this is all a compiler thing, we typically put all of this in the header file and not in the CPP file. And you will see that if you put these things in the CPP file, things will go wrong, and you will probably get linking errors because the compiler will then do replacing of code, basically. And that is why, when we use templates, we typically put everything into one file. Now, there are several things we can do with templates, and that's now what the next section will be about. You can have more than one data type that a class then needs to, or that the compiler then needs to make more concrete later on. So sometimes classes or functions use not just one particular data type that needs to be defined later, but 2 or 3 or even more. Well, there's no limit to the number of parameters for a template. That's why you just give them a name. The name needs to be different, of course. You need to tell them that they are classes or type names, but that's about it. So just like you can just have one, you can have multiple. You can also say that there's a default type for those. So if the user afterwards is only providing one of the template parameters, then the other one will be chosen as a character in this case, because we provided this as the default. It's very similar in syntax to how you have default parameters of a function or default parameters of a method of a class, right? So you just say this is car. You don't give, this is not a variable. This is like a type or a class. So it could also be a class in this case that we would have written here. But in that case, if later on, if what the class that is being defined here or the function that is being defined here is specialized towards only one parameter, then the second parameter will automatically be chosen to a character. However, if we then choose this as a particular thing, like the first one is an integer, the second one is an integer as well, then y data is then an integer. Okay? And also there we use from right to left this notation. So the right ones are defaulted first all the way to the left if we provide defaults for one or multiple parameters. I think also that goes without, or it doesn't go without saying, but also that would make the most sense, just like with the functions. You can also have non-type parameters too, like this thing over here. So we can actually choose to provide a template with, for instance, a number, or a string, or a character, or a Boolean. This is not often seen, but you can sometimes use this. If you, for instance, say we want the compiler to put automatically a constant maximum number of our container, then we can do this in this case as well. And we provide it this way. There are some reasons for and some reasons against this, because there are other ways to do this as well. You know, if you have a class, why wouldn't you do this in the constructor, for instance? Also that leads to a very complex way to deal with templates. You can do actually template programming where templates call other templates, and that way you have like a Turing complete environment where you can program almost everything with templates while the compiler is busy. But that is also, again, a very fringe movement, not going to be seen that often. Also, inheritance can be done with templates. That means you can inherit from other templates as well as from non-templates. So that is what is written here. So basically, you basically, by saying here that we have a type X or a class X that we will use in our templates, and by inheriting from another class, a superclass or a parent class, you can use this template for both of them, right? And for non-template classes, you can do this as well. So basically, if you have a class by yourself and you know that this will be an integer queue and this is what you want to have, you don't want to have the compiler later on specify this, then you can program this in your specific way, but you can still inherit this from uqueue that is specified towards an integer, for instance. And that way you can have integer queue, have new methods or new attributes that are being added that you would like to have for your integer queue. Also, that I think is making quite a bit of sense. This is also a nice thing. You don't always need to produce those types. So when you have a function, like our old maxof function over here, for instance, and it is very clear that what you're giving to this function are integers, remember, these are two constants and they're of type integer, then why would we need to explain this to the compiler? If only this compiler would be smart enough, it would know and would be able to deduce this. Like in many cases with auto, and in other cases, and from version 17 onwards, you can actually do this. So both these two lines, as well as these two lines, will do exactly the same. And also there, the trick is that the compiler here will see through the parameters that we're dealing with the function using integers. Over here, it will see that we're dealing with the function using characters. And therefore, this will return a character and this will return an integer. And that's the deal here for this example. And that makes our life, of course, a lot easier, or our code a lot shorter, and a little bit more implicit, of course, as well. And also there you will have then, of course, problems or potential problems if you start using different things here. So if this was not an integer, but a float, what would happen here? And also there, you know, there are things that can happen and things that won't happen. But also there, my recommendation would be to always stay type safe yourself. Use only constants in that case of the type that you already want to use over here, and then there's no problem through conversion. Yes, template classes, so classes that use templates can declare non-template friend classes. That is one possibility, or functions. A general template friend class or function, or a type-specific template friend class or function. So those are the three possibilities. The last one I think is the most interesting one. So here we have our class A, which is using a particular template. And here I renamed them, but you can actually use exactly the same. So here I renamed them to U over here. And U over here is being used by our template class B. Right? So we say in our class A, you can use the private data class B. So class B is able, since it's a friend of class A, to use data over here, even though it's a private attribute. I think that is, meanwhile, quite well known. So when we have our class B, we can, through its constructor, also create an object and then write out its data. And the fact that we can write out this data is because it's a friend, and because it's a friend, it can have access to the private data of class A. So when we then construct our object B of template class B using a particular template, using integer, we in that case will immediately, or can immediately then also create class A as an integer and gets access to this class A's attribute. Okay? I would recommend to go through all those examples. I think we have 9 examples meanwhile in this templates directory. I think they're all interesting. Okay, then what I've kind of postponed up until now is the explanation of operator overloading, which is not that outlandish because it's kind of the same as function overloading, except that you use the special keyword and you overload operators that already exist in C++. That means any operator that we know, so plus, minus, and all the things we've seen, including our spatial operator, all are overloadable. So you can depending on the data type of the parameters that you give to this operator, also define what this operator does yourself by just redefining this using the operator keyword. And this is almost the same as if you're overloading a function. That's why it's not that completely new, I would say. So in this case, we would have our class A, for instance, which has a public attribute A, which is a character. And in its constructor, it basically can take a character and then fills the value into the attribute. That's all this very simple class does. And if we then have an operator using this class, so using two parameters of this class, then if we would have then an object of class A plus an object of class A, then this function would be called and would return this particular data type over here, which is our string class, or an object of our string class. Okay? So that means if in our main later we would create two objects, A1 and A2, and we fill those with an A and a B character, then we can do this. And this would in that case be controlled through what we define this as. If we wouldn't do this, this would be problematic. Because class A over here, or objects of class A, for that we don't have the operator plus defined. And this is what your question earlier was about. If that happens, then our compiler will definitely complain because it doesn't know what to do. So in that case, we need to define what that operator does, and that is with this keyword operator. So see this as kind of a function that you now overload, so that once you have something that matches this signature of this function, like an operator that uses two objects of class A, and that is what is happening here, and then what it's returning is a string, which is okay for this operator over here, everything is fine and the compiler won't complain. Okay, so that is what is being concretely implemented here. And this operator then allows us to create new functionality. Of course, if you do this, you need to always make sure that this makes sense. Like in this case, I have these objects of class A typically being characters, and I want to, if I do one character plus another character, then I want to concatenate them. That is what is happening here. So I create a new string. I concatenate the character A1 to this, and I concatenate the character of A2 to this, and then I return this string. So that is what is being built here and being returned by the operator. So as soon as in our main function we get to this point over here, this particular operator is being called, and exactly that string is being returned. Right? So that will then allow you to show, or will then, if you implement this, you will see that in that case the output of such a thing would be AB. And if you would normally do this with characters rather than this class, of course something completely different would happen. I hope you remember that a character is basically a number. So in that case, if you do A plus B, or A1 plus A2, and if both of them were characters with those contents, something completely different would happen. So that would be a completely different operator. Okay, here's another example where we use, again, the operator. And the operator is first being defined and then being used over here, or declared and then being used over here. So in this case, we have, this is the typical example of overloading the plus operator for a class. So we have a class that wants to contain complex numbers, which contain typically of a real and imaginary part. That's over here. Those are, of course, private. That's typically what you would do in a class definition. And as public services that you have is you can either create an object, a complex object, and then immediately have the real and imaginary initialized as 0, and nicer would be 0.0, 0.0 here, or you immediately provide the real and imaginary numbers here and assign those. And you then tell that this operator, this plus operator, it does not belong to the class, it's a friend. So that's a friend function or a friend method, as we've seen a few weeks ago. So in that case, this operator over here that is being defined can use a complex number object with another complex number object, or complex objects, to then return another one. So if you then have object of complex plus object of complex, then it returns, this operator will return another one, a third one. And this is very similar to the last slide. You create a temporary complex number that we can do. It basically has a zero as a real and imaginary part. And then, as one tends to do for complex numbers, you add the real components and the imaginary ones. And then you return this. So that's how an operator will be completely redefined for a particular class as a friend function. And the new thing here is that it is a friend function and therefore can access the private data that belongs to complex. If it was not, if this was over here public, we would not have to declare it as a friend here, and we would just have something as before, right? That's the difference. But that's why friend methods are quite important, because this allows operators usually to access directly private data of classes for which they have to operate on. And this is, of course, one of the main usages of friend methods. And that's, I think, what I already hinted at when we had the friend keyword, and I hope this kind of solidifies what we see today. Okay, then we can also have conversion as an operation, because it is, in a way, an operation. And that is also interesting to note, I think, so therefore I'm going to also show that. So we have our class fraction, which kind of represents a fraction in the two components, right? At the top, the numerator, at the bottom, the denominator, as you would write. So the 7 and the 9 in that case. And we would have this class just store these two numbers rather than the floating point that it represents, or the floating point value that it represents. So we would have, in that case, our fraction constructor, where we basically the only way possible to create an object of fraction is by saying which number is the numerator and which number is the denominator. Those are then being stored over here in our private attributes. And we would, in this case, create an operator that belongs to this class, which is of type double with the braces here, the normal braces. And this means when it's converted to a double, only then we compute what the division of these two numbers would be. So we take our integers, we convert them to doubles explicitly. We can do that. That is explicit conversion. Then we have two doubles that we divide, and then we return this double that is produced over here, right? So that is what is being done here, and then we can actually then create an object of this particular class. So 7 divided by 9 can be created this way or instantiated this way, and this value the value that we have over here will then implicitly already trigger this conversion, because value is a double, and this assignment operator will then make sure that what is here is then explicitly being converted to a double. We could have also done this over here. We could have said explicitly convert what our fraction object is to a double. Then it would do this, but this would be exactly the same. This is kind of with an extra step to our assignment operator, but it will do this conversion and therefore will call this operator. And therefore, this will indeed then print out the double or the floating point representation of 7 divided by 9. Okay, so also this is an operator. Good, I mean, that was kind of a side track because we're still actually with templates, but operators and templates are very close to each other, as you probably would have guessed already to the examples. And that's why I now show one more thing with an operator. And one of the operators that has done for us loads of things already is this left shift operator. So also that one we, in this case, use. So we have our class, which creates or which has a template over here. And hopefully this template is then compatible with our operator. In this case, it will be, because this operator can actually do quite a lot. So we have our constructor over here, and we basically say in our constructor, we immediately then write the attribute through our constructor, and that's about it. So this is a fairly simple class, which is templated and using t as a parameter. And then together or parallel to this class, we use the operator of our output stream together with this particular class. So we have here a different number. We could have used t here as well, but we use a different one where we have an object of this particular class, my class, together with the output stream, which then outputs something to the output stream yet again. And what we do, and that's something that kind of is an implication of streams, as we saw last time, we put this particular thing on our stream. And if we put something on our stream, we hope that this is a character, of course. Right? That's, I hope, what you remember. So what we can do then at runtime is decide that we need an object t, which we immediately initialize as a character, explicitly here, although we could have left this away if we compile this in C++17 or later, if we then provide here a character, of course. But if we do this, then we're definitely, or it will definitely work. And then we can indeed use this with our left shift operator for streaming this to our output console. Okay, so these are typical things you then do with templates. You can have then not only templates of classes and templates of functions, but also templates with the operators using the functions and the classes. And all of this together might become slightly complex, but also very powerful as a construct and as a tool. And then we finally come to STL. STL stands for Standard Template Library and is huge. I would never dream to say that I know most of STL because it's also constantly expanding. But there are very important elements, very cool elements that are grounded, that have been there for a very long time, that people have worked on, that made these things very efficient, and that definitely should not cause us to reinvent the wheel all the time. So that's why I think STL is a very important thing to dig into. And that's what we're going to do from now on as well. So STL is a combination of using template classes, and that is a very big part of it. So just the way we did this for our two different types of implementations of queues, we can do this for any type of container that we would like. And there we will see several. So we could do this for an array because our typical C array is quite restrictive. So we could create, for instance, or we could have from STL an STD array. And this array is a lot more powerful. It will have methods that allow us to do a lot more. There are stacks, there's lists, there are vectors, there are queues, maps, and so on. Loads of things. I think the list is very long, so that's why I put etc. here. At the same time, when you have those template classes, you can also have algorithms for those containers, for instance, sorting them or searching in them, or doing other things that typically algorithms would do. Traversing, if these are graphs, for instance, or trees. All these things are possible. What we also think of when we use STL is iterators. So typically when you have a container, you have then iterators that move in that container. Think of the queue. There we would typically only have access to the head and the tail of our queue. But for other containers, we might want to move through the queue. And also there are ways that we can address elements, and those are done typically through iterators. So we go from one element to another, or we can point to these elements of these containers through these iterators. And then we have another thing called function objects or functors, of which I will just show in a second or in a few slides. And one example, and there are many more, which I think is also very important, and it's something that I think in the beginning gave a couple of hints on as well. And this is kind of a library that you can include, that is automatically included when you, for instance, include IOStream already, so you don't have to include that much more, apart from the actual container that you're using. Like if you're using a stack, then you do include stack, and then you have std stack, and then you can use this container. That's more or less how it works. And all of this is with templates. So basically all of this is kind of independent of the objects or the classes that you're using, or the types that you're using. So, and that makes it really powerful. That means all of those things are typically as efficient as they can be. If you go to the reference works of the standard template library, you will see also for all the methods how efficient they are, what the time complexity is of doing a particular method. And typically that is what it's maximized towards. So here's one example that we haven't seen yet, or I'm not going to see the queue now, but for the vector, for instance. A vector is the same as a dynamic array, but a dynamic array that also resizes as you're adding or removing elements, which a dynamic array doesn't, or we haven't done this for a dynamic array as we've seen up until now. So basically, this is then now template definition, right? We can create a vector object where we use the type double. We call this my vector, and then we can immediately call this with a particular list. So we have here a list of 3 doubles. So that's how my vector will be initialized. It will have automatically 3 elements, 2, 4, and 7. We can also do this differently. We can also say I want a vector, and I want to have so many elements, and I want all of them initialized with this particular value. That's another constructor of our vector container. And what we can also do is construct through copying, right? So in this case, we have a copy constructor. We say basically, if we pass my vector from up here, then we create a new vector where our data is perfectly copied, deep copy, into our copied vector. And we have 2, 4, and 7 to our availability, or the contents of this particular container over here. It's not pointing to the same data, it is copied data. Right? That's the important part. So those are potential ways to create a vector of our vector container class. And here's an example of how you would do this with a couple of methods that you would have then to your availability. So in this case, we use strings rather than doubles because a string is a class. At least we will use classes. So exactly the same denomination. We basically create here name, which is an object of type vector, of our class vector, which is a template class. We fill it in as string, and therefore, and we also construct this with a list of strings right here. That means this list of strings is then being copied into name, and that is what name then contains as a vector. And then we can look at the size through the size methods. We can look at the maximum size potentially possible here. You would typically get a very, very large number. We can check this. This is example 7. So if I have it here, I can compile this. And that works. There I did not make a mistake. So basically, this would be the maximum size of our vector that we would have. So we filled it with 4 strings, but we would have still a bit of space available in our memory. And whoops, I went one too far. And also we could have the capacity. Now the capacity and the size is slightly different because sometimes you can reserve space, but you don't have to fill in all that space. Think of the queues, the first implementation of our queue. So therefore, we have, again, different methods to manage all of this. Now, the next thing is the iterators. So typically, we always have iterators as well, which are typically member functions or methods that belong to our class and returning these iterators. And those are then being used typically with auto in a for loop. So what this returns is actually none of our concern. It's of a special type called iterator, but think of it as kind of like something that happens to be working like a pointer that points to an object in our container somewhere. An iterator that iterates, jumps between elements of our container. So this is not an integer or something else that we typically would have in a for loop. Now this is something that our compiler will decide for us or automatically will derive. And we'll say E in this case, or I in this case, is returned by the begin method of our name. And this will be, in this case, since it's a vector, returning this John element over here. And then we say I should be smaller, and that is already strange, but I is an iterator, we can do this operator has been defined for this, then the end of our name. And the end of our name would be Smith over here. Because a vector is not sorted automatically, there are other things that are, but in this case, this would be the thing that begin would iterate towards, and this would be the, what end would return here over here. And then we can also increment our I, which again is not an integer, it's an iterator. So we iterate over our container, and then we can, by dereferencing it, and also this is not a pointer, it acts like a pointer, think of it that way, and then we basically send this to our output. So this string that will be eventually then be outputted here will be printed to the console, as you can see. And that is what is being done over here. Now we can insert, that is insert is another method that we have for our vector, and which makes it different to an array in that case. So we can insert new things, and we can tell it where to insert. And we need also there an iterator. So this name begin is our iterator, and we can add 2 to this. And again, we then change our iterator. And we can then say the string Tom should be inserted in our vector of names, right? And now we have not 4 but 5 of them. And if we then print out those, and this is a new way of printing or of doing the for loop. We've seen this, I think, as an extra when we talked about for loops. This can be done again since I think version 17. We can then iterate over all elements of our container name and print these elements out. And since we use an ampersand here, we don't need to dereference. And that's the difference here. I hope you still kind of remember that. And as you can see now, there's lots of elements from the past couple of weeks appearing. But also this would then be printing out all the names in our vector, including the one that we introduced over here. So note that now we have a longer list and that Tom is implemented right over here. So we went to position 3 and inserted there a new name in our vector. Okay? So that is what a vector does. Completely different is a map. You might, I mean, if you often do things with Python, you know maps probably there already. Also, that is a container. Happens to work completely different. It works with pairs that contain a value and a mapped value, or a key value and a mapped value, where you cannot have mapped values that have the same key values. So they need to be distinct. And you can also initialize through this initializer list as we had before. So I can have a map container over here, and for a map container, we always need a pair. And for those pairs, we can have the same, but also different types of types. So in this case, I use for our key value an integer, and for our mapped value, I use a string in this case. Perfectly possible. So what we will have then is I will have 1, 2, and 9 integers, and Anne, Ames, and Asa as strings, right? And these pairs are now contained in our container. And our container will kind of magically use these and store these 3 in the way a map typically works. And the way it typically works, or you will see in a second when we output things. And we can do this in a different way. We can say we want, and in this case we have now the key as a string and the mapped values as integers, a list of students where we then store, for instance, for a particular student with this operator here, the square braces operator, the particular value operator, the value that belongs to this. So in this case, it is exactly the same as inserting a pair where the first element is Aaron and the second element is this particular number. And this way you then can start adding particular pairs to your map. Also, that is a way of doing things. Now, since C++11, we can do this way. That's what we showed earlier as well. So when we have a map, we can just iterate over all the elements. And then with .first and .second, we can have the first component of that pair and the second component of that pair. In this case, this would be the key and the value that would belong to this pair that is an element of our map. However, since 17, you can also do this, which is a lot, I think, nicer and more elegant to display this. You can just say we have this pair key, val, so the key and the value, and we iterate over our container students and have these two immediately as our two values. So if you print out, the key in this case for our students will be the names, and the values will be the student IDs that will be printed out one after the other. And with the same for loop, but a different notation, you'll basically, you can then iterate over these maps in a very short and brief way of mentioning this. So these are, I think, very elegant ways to use, first of all, a container from STL together with iterators, because in the end, what happens here is that we have iterators going over these, and then changing, adding, and using these containers. Here is another example that uses exactly the same thing, but that can be, again, downloaded by you. It's example 8. And you can see that both of them do exactly the same. So what I added here is that there's, of course, also an insert, or not of course, but there is also an insert method or an insert member function that belongs to our template class map, where we can insert a pair in this particular way, or we can insert a pair by saying explicitly this is a pair. Pair is another class that we have to our availability, where we specify what type this is, and then give the pair in this notation, which is also quite a nice notation, I think. And it's just a matter of taste, I think. What is the nicer way of adding things in this particular map? But that is up to the programmer. All of those are possibilities. And they actually do more or less the same, except that here things are constructed on the way. Okay? Then I have time for one more thing, one more element, and that is going to be one example of those functors, which is necessary for instance, transform. And transform is basically a function that you can use, that you can call, that is in STL as well. So you would have to your availability straight away, where you can release a function on a particular data type or container. So in this case, for instance, I would have a very simple function that takes an integer and then increases, returns the increment of this x. This is a very simple thing, a bit of a dummy example because there's way more efficient ways to do this. We have now an array, just an array. I'm not using a very complicated container here. I could use another container, but it would be the same. And now I can use our transform to go over this array where I just have to say where it needs to start from, where it needs to end, and where it needs to start from where I'm going to transform into. And I'm using the same array to transform into, so I'm going to override exactly this array. And then I can use this function on exactly the elements of array over here. So this is the way to say increase every element of our array up until the end of our array, if this array is 3 elements long. And then we can again output this, and you will see that in that case our original array has elements that are all incremented by 1. But that is a very simplistic explanation of our transform function. Now this is the unary use. You can also do this using 2 containers. And again, you can use this on any type of container that STL provides to you, or most containers that STL provides to you. So you can have vectors, you can have arrays, you can have queues, you can have loads of things for which you do any type of function. You can provide any type of function. And of course, since you provide a function, we can again revisit our lambda function. And that's why I added this particular example as the last one we'll see today with our vectors that we started with in STL. So I add a vector, or I create a vector object called A and initialize it as this. Actually, this can be also the normal braces. That's what I typically do. I have a vector B, which I initialize as this. And I have a new vector C, which I don't have initialized yet. That is what is happening here. Over here, I don't need to say that these are doubles, because that is what is implied already. So in the background, these are template classes, so you would need to say what template you're using, but since these are doubles, C++ knows what during compile time to use here. Here, this would be a problem, so here we need to explicitly say that C is a vector with its elements being doubles. Then we can just define a particular floating point, n, which we have given some value, and then we transform these two vectors into the C vector. And that is the non-unary way of using transform. So transform, again, is overloaded several times. So the previous slide shows it for the most simplistic form. This one is when you have two arrays. So we have our array A from beginning to the end. Then you have array B from the beginning. And what is implied there is our array B has the same size as array A. And then we basically say here to an iterator is that we're going to insert at the end of vector C. And vector C is at the moment empty, so it's going to append to vector C the new elements. That is the output. And then the function that we're going to use from our transform is this particular lambda function. And this is the new little bit of new information that you had on top of what we've seen already about lambda functions. So remember, lambda function is kind of an anonymous function. It doesn't have a name, but it has these two parameters, double x and double y. And it returns x and y, then divided by n. This n we don't know over here, but through this over here, we can say that all the external variables that are used in lambda and that are present in the scope where it's being used are copied in by value. That means in this case, this particular n can be used by our lambda function here, because it is right here, right? And that equal sign over here is saying all the external variables are copied into this lambda function that are necessary by value. If we would have wanted to copy by reference, and also this would be possible, you can try this at home, you can replace this equal sign with an ampersand, and then it would still work, right? We could, in that case, not copy the value 2.7 over here in this particular function. We would just take the exact 2.7 that belongs to this n, and then use this over here. There would be no difference. So both of them would be necessary. But in the end, we would have then this function which takes two parameters and then returns this calculation out of those two parameters. And that is then being launched on A and B's elements, right? So it takes the first element of A, the first element of B through those iterators and gives those as doubles to this function. And this function then takes n as well as these two elements and then calculates this over here. Okay? It's a little bit complicated, but it's very powerful and it's very time-saving, or especially space-saving, right? Because if you would have to do this with nested for loops or several for loops in a row, this would become very unreadable or very long at the same time. If you know how to read a transform function, and there should be an std in front. I made several errors, I think, here, but here should be std, : transform. Then it would be quite small still, right? That is, I think, what is the message here. Then you can print this out, and you will see that this calculation is done on A and B and put into C. And like this, you can do loads of things. And of course, not just arithmetic operations between different vectors. You can do this as, of course, matrices or images or very complex data structures that you can think of. Right? That is the idea here. Okay, so that is kind of just a tip of the iceberg of what STL can do for you. And to learn more, those are 2 reference points that have everything, but of course, you can use any instrument to you available to explore all the things that are in STL. Okay, no more questions? Thank you very much. We'll see each other next week at least.